Hello, this is Brian Washburn, and today I'd like to give an introduction to the Fourier integral, or is also called the Fourier transform. Okay, um, so we've talked a lot about a lot of different mathematical methods in this class, and every time I talk about them, I say, "Well, this is really important. You should know this." And I say that for all this stuff, and obviously, if it's important, I'm going to talk about it. But the concept of a Fourier transform and Fourier integral, for example, for my line of research, is really important. Out of all these methods that we're learning, that includes solving differential equations, the concept of a Fourier transform is essential to the research I do. And it's used throughout many areas of science and engineering. It's a real important concept. Okay. Unfortunately, it's a difficult concept, and we're not going to have the time to fully develop it. I mean, I could spend half the semester talking about the Fourier transform and not really get into the meat of it. So my point here is to extend what we learned about the Fourier series into the Fourier integral, okay, and to give you a true introduction to this thing, okay, so that way when you see it later on in your coursework, you can understand the importance of it, okay. Now, the other thing is normally when the Fourier integral or transform is introduced in either a math class or physics class, they usually do a fairly terrible job introducing it. Okay, for example, whether it be a math class or a physics class, they introduce it as a mathematical tool or construct, and they teach you how to use the tool, but they don't really teach you what it means. And so what I want to try to do is give you a better feel for what the tool means and in terms of a physical context. That's really what my point is here. So let's review. So I want to focus on talking about the Fourier series of a square pulse. So we did this in class before, and what I have is a periodic function in time that's a positive square pulse. Okay, that's what I'm showing you here. The function has a period tau, and each pulse has a width delta tau. Okay. And last time what we did was we derived the Fourier series of this. It's equal to a constant a naught plus a sum, infinite sum of cosines. Okay, a sub n is the coefficient, and then n times 2 pi divided by tau. Okay, that is the. Now remember one thing. We also define the variable omega. Omega is going to be equal to 2 pi divided by tau, and that is what I would call the fundamental frequency of this thing. Okay, so this is called the fundamental frequency of this periodic wave. Okay. Okay. So a naught is a constant, and then we can get all the sine terms. And then what we also did was we made a bar graph of all the a sub n's as a function of time, or a function of n. So this is a sub n for n number 1, 2, 3, all the way up. And we gave this thing here, we called this the spectral content of this repeated wave. This is the spectral content of this wave. And basically it's a bar graph. And again, the way to think about this is a weighted sum, a weighted discrete sum of cosines. Each cosine has a frequency n times omega. Remember, this is omega, so it might be better to write this as, instead of 2 pi divided by tau, I can write this as omega. So the argument looks like n times omega. So each frequency component has a frequency of n times omega. Okay, so for the nth frequency component, its frequency component is n times omega with a coefficient of a sub n. Okay, so I sum over those guys there. All right. Okay, so that's what we have. Now, what I want to do numerically is I want to look at two square waves. Okay. And I'm going to look at first the example we did in class. And here I have a period of tau equal 1 second. The width is 0.1 seconds. And I'm going to express my Fourier series in 100 terms. Okay, so I'm going to get something that looks like this. But then what I'm going to do is I'm going to write another square wave. Okay. Except I'm going to change the period. I'm going to change the period to 10 seconds. The width is still 0.1 seconds, and I'm going to represent that as 100 terms. Okay, and then we're going to express more terms. So let's take a look at that. Okay, so I have my same program Fourier series that I use to calculate the Fourier series for a square wave. And here is notice that the period, the first pulse occurs. I'm looking at one pulse out of the sequence. occurs at time 1 second. Okay, and that's tau equal 1 second. And then this is my representation of my square wave. So it's not perfect, but it looks okay. And then this is a bar graph of all the a sub n's. And again, I'm using 100 terms. So I would say, okay, this is, I probably should use more terms, but it looks okay. It looks pretty square. Okay. So now what I'm going to do is I'm going to show you the Fourier series representation of the same periodic train with 100 terms again, but now I'm going to set tau equal to 10 seconds instead of 1. Now let's take a look at that. That's these two graphs here. Now take a look. This graph here, that doesn't look square at all. So this is a poor representation of the square wave. Okay, even though I have 100 components, I still have the same number of spectral components. Okay. Now if we plot those spectral components, notice that I go from 0 to 100, but notice that this thing kind of goes down to here. Now compared to what I had, now let's take a look what we had before. What we had before was we had a nice square wave. This came down, up, and down, up. Okay. This guy here have a poor square wave. It just comes down, never comes back up. Now, if you take, now again, there's still 100 frequency components here and here, okay? But if you notice that, if you take, going back to my notes, think about the frequencies of those spectral components. The frequencies of the spectral components are going to be n times omega, okay? Where omega is equal to 2 pi divided by tau. Now, for the first case, if you think about this case here, okay, well, what I can write here is that, well, 100 times 2 pi divided by 1 second, okay, that gives me a specific frequency range of 200 pi, or 2 pi times 100 divided by 1 second. Okay, that gives me a specific frequency range. However, if I do the same thing here, I do 100 times 2 pi divided by 10 seconds, notice I'm going to get a tenth of what I had before. Okay, and that is shown in this graph. Notice that here, even though I have the same number of frequency components, my spectral range is smaller. Again, my spectral range is going to be n times omega. Well, for this case, n times omega is, again, mega here is just 2 pi, is going to be a bigger number than for this case, where in this case omega is going to equal to 2 pi divided by 10. So even though we have the same number of spectral components, our spectral windows are totally different. Okay. So then you may ask yourself, well, what do I need to do to make, so this looks good, this looks poor, what can I do? Okay. Well, since there's a factor of n, 10, let's make the spectral components bigger. So instead of using, so how can I do it? Instead of using 100 points here, let's do 1,000 points. Okay, so what I'm going to do is I'm going to change that 100 to 1,000. Okay, and we'll run this. Okay, so that took a little time, but here are my results. Okay, again, what I'm showing you here is this is the square pulse that has a period of 1 second. Okay. And this is its frequency components here. Okay, again, each spectral component is separated by omega, and omega is 2 pi divided by 1 second. Okay, now I run the other one with 1,000. Now take a look at that. Now notice that, hey, this looks like that, that looks like that, that looks the same. So it looks like, hey, I did now with 1,000 points for the tau equals 10 seconds, I have a better representation of my Fourier series. And see here, hey, look, the wiggles kind of go up and down. So this shape here looks like this, but the main difference is that, well, I can see gaps between them because the spectral components here are farther apart because of, remember, the fundamental frequency here is 2 pi divided by 1 second. The fundamental frequency here is 2 pi divided by 10 seconds, so the spacing is closer, so I can't see that here. But with 1,000 points, I have a good representation of my Fourier series. Okay, so notice that. So in the end, let's kind of summarize, what I showed here. Okay, so for tau equal 1, I have 100 spectral components. Okay, and the fundamental frequency is 2 pi divided by 1 second, or 0.628 rads per second. My approximate Fourier transform looks okay. But then if I use 100 spectral components, and here my new frequency, my new fundamental frequency is it's 2 pi divided by 10, or 0.6 radians per second. it looks bad. Now if I add more spectral components, I got something that looked better. Now let's take a look at that in more detail. So if I go from tau equal 1 second to 10 seconds, first of all, omega, the fundamental frequency, decreases because what I do is, before I had 2 pi radians per second, and then I'm going to have a tenth of that as omega goes from 1 second to 10 seconds. Okay, so that's again going from 6.28 radians per second to 0.628 radians per second. Okay. Also, I noticed that I need a larger number of points to get a good expression. Okay, so I had to go from 100 to 1,000 for tau equals to 10 seconds. So really, if you notice, there's some constant here, and the constant is going to be, well, n times omega. Okay, n times omega is, I would call that the spectral window. Remember, each spectral component is separated by the omega. The total window is going to be the number of components times each little step. But n times omega is going to be equal to n times 2 pi divided by tau. Now, if that remains a constant, then I'm going to get a good shape for my Fourier series. Okay, and notice, in the end, what I did to get a good Fourier series for this guy, at 1 second, 100 points. 100 times this gives me 628 radians per second. Now for the other one where I had tau equal to 10 seconds, all right, I don't need 100, I need 1,000, but still when I do this product of 1,000 times this, I get the same number and I get a good shape. So I need the same spectral window in order to get a good Fourier series representation. Okay. Now, what we're doing here is we're showing the behavior of the Fourier series as tau gets bigger and bigger and bigger. All right, that's important. So you saw that behavior. What the heck does this have to do with the Fourier transform? So let's take a look. All right, now this is the problem. Say I don't have a train of square pulses. Say I have one square pulse. Okay. Can I write the Fourier series of that? Okay. Or actually, a better question is this. What are the spectral components of a single square pulse? The Fourier series gives me the spectral components of a train of pulses. What is the spectral components of the square pulse? To answer that question, you might say, well, can we write a Fourier series of this? The answer is no, because it doesn't repeat. Okay. Or really, does it repeat? Maybe this pulse here, maybe this is a train of pulses. It's just the next pulse comes at t equals infinity. Okay, that's kind of crazy, but that's the gist. Okay, so a single pulse looks like an infinite train of pulses where I have to wait infinitely long time for the next pulse to arrive. So that gives me a method to go from what I learned about Fourier series to this Fourier integral. And in fact, that's what I just did in the code. In the code, I just went, instead of going from 1 second to infinity seconds, I went from 1 second to 10 seconds, but we're going to see similar behavior. Okay. All right. Now, in order to do this, I have to be a little bit more mathematical. So I'm going to rewrite the Fourier series in terms of the Euler relationship. Remember, Fourier series is sums of sines and cosines. So what I can do is I can say, okay, an Euler relationship says that e to the argument I, that's imaginary number, omega t equals this thing here. That's Euler. My Fourier series is a sum of sines and cosines. I can rewrite this sum in terms of a constant Cn times e to the, that should be little n omega t. And again, what is omega? Omega is 2 pi divided by tau. That is a value, a discrete value called the fundamental frequency. And then Cn is how I calculate, instead of having coefficients an and bn, they're all compiled in Cn, where I have to do a complex integral over one period. Okay, now what I'm going to do is I'm going to take this guy here, sucker here, stick it into here and rewrite it here. So again, let's take a look at Cn is everything in the brackets. And notice, in order to calculate Cn, I have to integrate over time, but to distinguish that time from this time, I call this tau. And so what I have here. Okay, so again, this is just a Fourier series. Now what do I want to do? I want to look at the behavior of this expression here as tau goes to infinity. All right. What happens? Well, first of all, we saw this before. Remember when I went from 1 second to 10 seconds, the fundamental frequency got smaller. It went from 6.28 radians per second to 0.628 radians per second. So in the extreme limit, as t or tau goes to infinity, I expect omega to go to 0. Or really a better way to say it, not to 0. Omega goes to something that's infinitesimal small. So omega goes to d omega as t goes to infinity. Okay. Now, what also happened, remember, as I increased tau, I needed more points, big N, okay, or little n I'm using here, to get a good representation of the Fourier series. So I expect that as omega goes to, this omega goes to 0, this guy should get bigger so that the product between the two is going to be a constant value. Okay? And so I'm going to recall that product omega. Now omega now is not a discrete number, it's a continuous number. Okay, it's not a discrete thing, it's a continuous thing. Okay, so I'm going to call this, now sometimes books would call omega that discrete value, omega naught, and n times omega naught's omega. Following your lecture, your textbook. So this is kind of a poor choice of notation, but it works. Okay, so again, this guy is a discrete number. This is a discrete number, and the limit as tau goes to infinity, this goes to infinity, this goes to 0, but the product is going to remain a constant. I'm going to call that a discrete variable omega. Okay. Then the final thing, and going back to remember, this is my expression here. Notice I have a sum of 1 over tau. In the limit that tau goes to infinity, this discrete sum becomes a continuous sum. And since tau is, omega is 1 over tau, this thing here is going to go to omega. So in the limit that I get, so again, what I'm doing is I'm trying to look at this expression here, in the limit that as tau goes to infinity, with these three factors going on at the same time. So let's look at that final expression. Okay, so again, this is what I have. I'm going to go as tau goes to infinity, n times the fundamental frequency. This is a discrete number goes to a continuous number, omega. The sum over all n's, 1 over tau, goes to an integral over all frequencies. And so then I'm going to rewrite this thing in that context there. And so instead of having, now I have an integral. This sum here becomes an integral. And now what I have is this thing here. I'm going to call that f of omega, because when I integrate this over all times, I'm going to only have megas left over. Okay. And then f of t is going to be another integral of this times this. So now I'm going to define the Fourier transform or the Fourier integral. There are two of them. One transform basically says if I have a function f of t, I'm going to define script f as an operation of doing this integral here. And that gives me f of omega. So that is an operation what I do. It's basically doing the inside of this guy here. However, to go back, if you give me f of omega, I can do another integral transform to get back, which I call that the inverse transfer. Script f with a minus sign of that gives me this. So this guy here has a name. This is called the spectrum, or the frequency domain representation of the signal. This is called, the time domain representation of the signal. Okay. All right. Now let's talk about this in a little bit more physical context. So this is if I summarize this, okay. What is f of t? F of t is my non-periodic pulse, just that single square pulse. F of omega is called the frequency spectrum. It represents all the frequency components associated with adding up sine waves, sinusoidal waves, to create that pulse. It is the spectral content of that time wave. That's what f of omega represents. And then what is this sum? Well, think about this. This term here is sinusoidal functions of frequency omega. This guy here is a function of omega. So really when I add this, I take this times this and I add up. So this is kind of a weighting function that weights for a given omega. It gives a weight for that omega when I sum up all frequencies. However, when I add them, it's not a discrete sum, it's a continuous sum. So this represents a sum over all sinusoidal waves, e to the I omega t, weighted over all omega, weighted by this function here. Okay. Now, typically in a math class, what they would do is they would just define the Fourier transform. And the way they do it is the first thing they would show is they would show you this. This is the Fourier transform. given a function f of t, I can get f of omega by doing this integral. Okay. And then if I want to get f of t back, I take my answer from here and stick it in the inverse transform and get the answer back. That's the way you would be introduced into physics or math class. However, this is a much more physical representation. Again, this thing here represents the spectral content of the wave, and I add up all those sine waves that create a time-dependent wave. But the addition is in a continuous manner. Okay? That's the physics. Okay, if you can understand that, oh boy, that's great. Okay, so I'd like to end by determining the Fourier transform of a single square pulse. Okay, I call this square wave, but it's really a square pulse. My function is, it's f0 from minus delta tau over 2 to tau over 2. And so what do I have to do? I have to do the integral over all space of f of t. Now, most of it is equal to 0, so in the end I have to just do the integral. Okay, don't worry about the 1 over 2 pi's just yet. There's another factor I need to include, but just ignore that. I'll explain that in class. But I need to going back to my definition, I have to do, this is my function, which is 1 between minus tau over 2 to tau over 2 and 0 everywhere else. I have to integrate that over all omegas, okay? Or actually I'm doing so yeah, that's what I'm doing. So what I'm doing is I'm going to calculate, actually what I'm going to do is I'm going to calculate the Fourier transform, or I'm going to calculate f of omega for a given ft. All right, that's what I'm going to do. So here, f of t is this function here. I stick it into there. Now it's just the integral of an exponential. I can do that. And so here I get this, and I evaluate that at the bounds, and I get this. And you may say, well, there's an imaginary there. Isn't that going to be a problem? No. Using the Euler relationship, if I subtract those two guys, I get minus 2i sine. Okay. And so my function in the end, let's ignore the constant, looks like sine of omega divided by omega. Remember, this is going to be a function. Remember what we're solving for is we're solving for the spectrum, or f of omega. So f of omega equals this stuff here. Okay. Now what I get is I get a function that looks like sine of a constant omega divided by omega. That has a special name. Sine x divided by x is called the sinc function. And so then what I get is that's my answer. Okay. So let's plot that answer. Okay. So I have a Python program called Physics Fourier Transform. And all it does is it plots those answers. So this is my pulse, my square pulse, has a width of 0.1 seconds, just like we did before. Except instead of it being an infinite train of pulses, it's just one pulse. It occurs at times t equals 0. And then I plot the sinc function. And that's sine x over x. And notice it wiggles and it kind of comes up like this and wiggles like that. Okay, that's my result. All right. Now if you take a look if I go from here to here, notice it kind of comes up and wiggles down, okay? Well, what the heck? Remember when we did the Fourier series? Okay, let me do that result. So again, what I'm showing you here is this is the Fourier series of a pulse train with tau equals 10 seconds. Look at the frequency spectrum. It kind of goes down and up, but these are a bunch of discrete lines. Kind of comes down. It has these wiggles just the same as the Fourier transform. That is not a coincidence. Okay, I won't get into that here, but because they're both square pulses, okay, in some respects. All right. So this is the concept of a Fourier transform. And again, just really to summarize, again, basically what this allows me to do, understanding what this means physically, again, f of omega represents the spectral content of a wave, okay, of a single pulse. And if I do this integral, if I know the spectral content, I can get the function as time, okay. Now a lot of times when we do this in practice, what we'll do is we'll be given an f of t, and in order to get the spectrum, I can always do this. I give an f of t, I can get the spectrum, or which is called the Fourier transform. If I know the spectrum, I want to get f of t back. I do the Fourier inverse transform, which is right here. But I was talking about this integral here, and again, physically what it means is f of omegas depend on, it's some distribution of omegas. It's a continuous function. I add them up continuously times this thing here, which is sinusoidal functions, which is a representation of my time dependent field, which is a pulse. Okay, that's it. We'll talk a lot about this in more detail, and we'll do some examples. We'll see you later. Bye-bye.